Okay, so this is going to be the tutorial for this week's Excel. The last two questions on the third Excel homework cover this. They are how we would do hypothesis testing in Excel. Okay, so we have three different types of examples. One where we know the population variance and we have a sample mean. One where we have the sample mean but we only have a sample variance. And then one where we're dealing with proportions. Right? So the first example that I'm going to kind of walk through for us here is if we open that hypothesis testing Excel workbook, one of the sheets we have is female blank. So these are the two blank ones that I'll kind of work through, and eventually when we're done, we should have these, what looks like these completed slides here. But we're going to work through these. So get a little more coffee. So this first we're going to look through the example that I kind of had set up in the PowerPoint slides is, let's assume that we want to test the hypothesis that the average female height in the US is different than 65 inches. So we've got an assumed population variance of 8, and we want to do this test at the 90% level. So I have a summary of what functions we could use, but we'll walk through these. So I'm going to put this hypothesized, or true value, or my value that I'm going to be testing for or against, in this cell right here. And I moved it over. You don't have to do that. You can leave it original where it is. I guess I'll leave it there just so for simplicity. But what are the things that we're going to need? Well, we're definitely going to need to come up with a test statistic. So we think about the equation for our test statistic. In that equation, we're going to have a sample mean, a population variance, a sample size, and the assumed true value. So I need to look at this height variable, and this I have a data set of only the female kind of subjects or observations. So I can find the mean, taking the average of that height variable. Once again, select the first cell, Control-Shift or Command-Shift on the Mac, hit the down arrow, selects the whole column for me, nice and easy. Population variance. Well, here I can't. If I had population data, right, and if I could calculate it from the data, this wouldn't be a sample. I would know the population mean. Hypothesis testing wouldn't make any sense. So here it's just kind of a goofy example. Like I said, sometimes because we know something about the machinery, but somehow we know the population variance here is approximately 8, or that's what we're told it is. We can then find our sample size. That's always just using that count function and then selecting the variable that we want to look at. So count. So we've got a pretty big sample here. Okay. So how can I find my critical value? Well, the critical value, remember, it's the value that is the cutoff that gives you your desired alpha in the tail. Well, here we have a two-tailed test, right? So the area that's in each of my tails, well, alpha is the total area in the tail, so it's getting split into two. So my alpha value I can think of at the 90% confidence level, my alpha would be 0.1. I could even label this if I wanted to. So my alpha is 0.1. So how do I find my critical value? Well, if I know the area I want, and I want to find the z value that gives that to me, because remember, we have a known population variance, so we're dealing with that standard normal distribution. If I know the area that I want, and I want to work backwards and find the z value that gives me that area, I use that norm.s.inv function. Okay? So the probability I want was alpha, but for a two-tailed test, it was alpha divided by 2. Okay? So I've selected kind of the cell that I had alpha in, divided by 2, using that norm.s.inv. Now, one problem is going to be, for a two-tailed test, if I look up alpha over 2, well, alpha, we're always dealing with these small values, 0.01, 0.05, 0.1. We're always going to get the negative critical value. But for a two-tailed test, we know that we have pairs of critical values. So the way that I would like you to do this on your Excel assignment, and also just a good way to do it in practice, is we have two critical values. And so we can find the negative one by simply doing alpha over 2. But then I can make that positive, kind of show, okay, there's two critical values here. It's going to be the same value, but the absolute value. So use that ABS function to find the absolute value. Okay? So I've got these pair of critical values for my hypothesis test. How do I find my test statistic? Well, I can actually just I'm basically using Excel to do them to be a calculator for me. I want to take the sample mean that I found. I want to subtract the hypothesized true value. I'll then divide by the square root of that population variance divided by my sample size. Okay? So that's my test statistic. I'm just basically using Excel to be a calculator there. So I get a pretty big test statistic here. All right? Negative 15.8. That means this value is 15.8 standard deviations away from the assumed true population mean. The sample mean I found is 15.8 standard deviations below this assumed true value. So hopefully we can kind of guess what the p-value is going to be. Well, if we're looking for the area to the left of this, and then for a two-tailed test, well, the area in the lower left tail, we also have an upper right tail that was equally as likely for us to see sample means on the other side of that assumed true mean. So we'd have to multiply by 2. Well, if I know the test statistic, or I know the z-value, then I'm using the norm.s.dist function. I'm telling it that z-value, I want the area to the left here, since it's kind of that negative test statistic, and then I'm going to multiply it by 2. Okay? Because I have a two-tailed test, to get my total p-value, I have to multiply by 2. Notice 7.6 e to the negative 57. Anytime in Excel we see this e to the negative, that means move the decimal point 57 places to the left. This is essentially 0. So with a p-value of 0, we definitely know we're going to reject. Or we could think about if we plotted these critical values and then plotted my test statistic, this test statistic would clearly be greater than the absolute value of the test statistic would be greater than the absolute value of my critical value, or it would fall in my rejection region. So, let me try to kind of draw this one out. So, there we go. We'll get rid of what we had up here before. Really what we found there was, we're dealing with the standard normal distribution. Let me see if I can get this to autofocus a little better. There we go. We found the critical value was, what did I have? Approximately negative 1.65 and positive 1.65. Those are my critical values. So here's my rejection region. I found a test statistic of negative 15, which is going to be way out here, definitely in my rejection region, so I'm definitely going to reject here. Right? Or when I found the area to the left of that, or my p-value, that was approximately 0. Well, if it's approximately 0, and I reject if that p-value is less than alpha, well, 0 is less than my alpha of 0.1, p-value leads me to think I'm going to reject as well. So it doesn't matter which approach I use, I'm going to reject. Right? Whoops, I didn't realize I was typing in Excel there. So that's how we would kind of set up one of these. Now, I'll show you another kind of trick you can do. I don't know. I don't think I ask you, you don't have to do this in your Excel assignment, but one thing you could then start to do is say, all right, what's my rejection decision? So we'll say equals if. We'll use an if statement. So what the if statement does is you're going to check something, and if it's true, you're going to tell Excel what to put in this cell. If it's false, you're going to tell Excel what to put in this cell. So we have all this set up to calculate our p-value. Let's say, okay, look, if the p-value is less than, and let's say we're going to test it against this alpha value. Right? So if it's less than that alpha, I want you to put in the word reject. Now, when you tell it to put in a word, you have to put it in quotation marks here, so that's why I have quotations around the word reject. So tell it what you want to check. Is L10, the p-value, less than this alpha that's in L7? Second thing, comma, if it is, put reject, comma, if it's not, put, and I'm just going to put fail to reject here. Right? So check this, put this if it's true, put this if it's false. So here, I reject. Right? Now this is kind of nice, because we have everything referenced, Now look, I'm not very far away from the hypothesized true value, so why am I able to reject? Well, with a sample size of 3,661, remember, the standard deviation of our sample means is the square root of that population variance divided by our sample size. So when we really jack up that sample size, we're getting a really, really narrow distribution for our sample means, meaning that it's only likely we see values really close to whatever the true population mean is. So therefore, it gives us a lot more power in being able to reject certain values, right? So notice, I could even say 64.5, could I reject that? Well, this still pretty large test statistic, still really small p-value, sure enough I can. What about 64.3? I mean, that's really close to what I found. Okay, well at that point I start to get a pretty large p-value. I can't reject that as a possible true mean. I'm very close, I can't reject that. So we can start to play around with this and see what values we can reject, what values we could not reject. Okay, this is a kind of this if statement's kind of fun to see. Like it puts the words in there for you, makes it really nice and easy to see. Right? So we'll go to the BMI blank worksheet. We'll go through two more examples. So the first one, it's going to be very similar to what we just did, but we're going to be dealing with a sample mean, and now I don't know the population variance. So in the slides, this is actually the last one. Let's say we want to test for whether or not the average BMI in the US is greater than 29. And we're going to do this at a 95% confidence level. So I have all what we're going to do here kind of summarized, but we'll walk through it. Well, the first thing I need to know is, okay, I want to make a statement about the population mean. Well, what did I find from my sample? So I'll take the average of that BMI variable. So once again, Control Shift or Command Shift on the Mac down arrow, hit Enter. Okay, so I've got 29.49. I've got the hypothesized true value of 30, although that might be different than what I said in the slides. I said 29 in the slides. So let's stick with that. This hypothesized true value, let's do 29. Okay. The sample variance, well now, I'm not told what the variance is like I was before. I actually have to calculate it. So I put equals, oh, come on. I want you to be able to see this. Here we go. Equals var.s, select where I want to start, right? The BMI variable, Control Shift down arrow, or Command Shift down arrow on the Mac. I've got my sample variance. Sample size, I'll use that count function. Once again, select that variable. Okay? So I've now got, oh, it looks like I just got female BMI here, but that's okay. Did I have the male? Let's double check here. Yeah, I got the male sample on the completed version. So the numbers will be a little bit different on the completed slide because it looks like I forgot to copy over the male data. That's okay though, it's the same process, it won't really affect much. Okay, so I've got 29 as the value I'm testing against here. How can I find my test statistic? Once again, just use Excel as a calculator. You're going to take your sample mean, subtract the assumed true mean, divide by the standard deviation of your sample means, which is the square root of whatever sample variance you found, divided by your sample size. All right? So this equation, right, comes directly from things that we were talking about in the lecture earlier today. So where this comes from is here. Right? We said before, let me get this to autofocus. And so the equations that we're using, please focus, scroll on the camera, maybe. Start writing these and hopefully it focuses a little bit better. Oh, maybe? I don't know why this isn't focusing very well. So this is all we were doing, is we were taking these equations and basically just putting them into Excel because we had all the components where we could just select things in Excel. Right? I'm not sure why I'm getting such a glare on this. Hopefully, oh, there we go. All right, now we got it. So those are the equations we're using. So we're just putting those test statistic equations into Excel. and selecting where the values were for each component. All right. So I've got my test statistic. How can I find my p-value? Well, just like we did in the previous example, if I know the test statistic, and I want to find the area to the left or right of it, well here, before I want to find the area to the left because I had a negative test statistic. Here I've got a positive test statistic. I have a right-tailed test because remember I wanted to test for whether or not it's greater than 29. So I've got a right-tailed test. I want the area to the right of my test statistic. So if I use that norm.s.dist, well first of all, I can't use norm.s.dist because I only have a sample variance. When I only have a sample variance and a sample mean, I need to use the student t distribution. So I'll use t.dist. Right? I'll tell it my test statistic. I then can tell it my degrees of freedom, which is my sample size, minus 1. So we always kind of put this comma 1 for the cumulative option here. Now the problem is this is going to tell me the area to the left of the test statistic. I wanted the area to the right. So I can do this in a separate cell and do something like 1 minus this. Or I can just put it all in one cell and put 1 minus whatever the area to the left is, which is what this t.dist function tells me. Okay? So, and now this obviously isn't right because I've put it all in one cell, but I can do this all in one cell here. Okay? So I've got my p-value. How can I find my critical value? Well, just like before, instead of norm.s.inv, I can use t.inv. Right? The area that I want, I believe actually here, is it the 90% confidence level? I might have changed this in the slide. So it looks like it's 95% here. So I actually want, what? I'll put it right here. It's going to be 0.05. And I have my sample size minus 1. Okay. So that should work once I put that I want the alpha of 0.05, right? Now here I have a problem, okay? So I've got my alpha. This is the area that I want in my tail. But remember, I'm doing the right-tailed test. So I actually want 0.05 in the upper right tail. Just like that standard normal table, and the way that these work in Excel, the INV functions, the area that you're telling it, this probability, is always the area to the left. Well, if you want the area in the upper right tail to be 0.05, the area to the left of whatever value would give you 0.05 in the upper right tail, the area to the left would actually be 1 minus that. So I have to put in a 1 minus, right, whatever my alpha is. And now I get the same value, but it's positive, right? If I take that 1 minus out, I had the same value, but it was negative. Now, another way I could do this is if I just remember, oh yeah, this will give me the value. If I look up alpha, it'll give me the value, but for a right-tailed test, it needs to be a positive critical value. I could just take the absolute value of that as well, and I'd have the same number, right? So we can do this multiple ways. So actually, I'll put both of them in there. So we take alpha, 1 minus alpha, and then our degrees of freedom was our sample size minus 1. Okay? Get the same value either way. Okay? So now, once again, we could do kind of play around with this if statement. So rejection decision equals if my p-value, and actually this one will do a little bit different. This one will say if my test statistic, right, is greater than my critical value, which I had over here, put in the word reject, comma, if it's not, put in the word fail to reject. Okay? We hit enter. So here we had a small p-value, or we had a test statistic much greater than the critical value, so we reject. So let's say, what if we wanted a value that's a little bit closer? Let's say, can we reject 29.3 as the BMI? The BMI is, if we were testing for whether or not it's greater than 29, what we're assuming is that it's less than or equal to. Well, we found evidence that's inconsistent with it being less than or equal to 29, so we'll hit enter. At 29.3, my p-value, my test statistic is too small, my p-value is too large, I'd actually fail to reject. Right? So this is how we could set that one up. So the third and final example is if we want to test for whether or not the proportion of whites in America is less than the published percent of 63.6%. We want to do this at the 99% confidence level. So, yeah, and these are labeled correctly. I forgot to kind of relabel these. So this one was 95% level. This one was 99. Can't switch things around at the last second. But the completed slides, these match, or completed worksheets, these match up with the slides. And once we work through this, ours will as well. So how do we find our test statistic? Well, this we had a slightly different equation for. Right? If we go back to the slides instead of me trying to use the board since it keeps taking forever to autofocus. Let's go back here. Here was our test statistic equation that we needed. So take our sample proportion minus the assumed true proportion, divide by the square root of the assumed true proportion times 1 minus the assumed true proportion, divided by sample size. So we need the sample size, we need assumed true proportion, we need sample proportion. So how do we get that from this? Well, I have this variable, which you can ignore the if statement that I used to create this, but it basically identifies whether or not the individual is white or non-white, right? So 1 if they're white, 0 if they're not white. What we talked about, if I wanted to find a sample proportion, it's really just a mean of a binary variable, right? So I can take the average of this binary variable where it's a 1 if they're white, 0 if they're non-white, select the whole thing. This gives me the proportion of my sample that was white. I can find the sample size by using that count function, selecting the whole variable. Right? So I've got my sample proportion, my sample size, and I also have that, and I think it was actually 63.6, I guess we could even say. It's going to be real specific with this hypothesized true value. Well, I believe I had, was it less than that, so it's a left-tailed test. My alternative hypothesis has a less than sign, so I'm assuming that the proportion is greater than or equal to 0.63. I found something that's very inconsistent with that. I can guess here. I'm probably going to have a very large test statistic, and we'll talk about why in just a second. So I don't know why X is down here. So my test statistic will be take my sample proportion, subtract the assumed true proportion, divide by the square root of an assumed true proportion times 1 minus that assumed true proportion divided by my sample size. Okay? I'm just using Excel to be a calculator for me here, and I have all these values. I can take them out to whatever decimal I want. I don't have to worry about rounding. So now I've got my test statistic. Well, this is a huge test statistic, right? 18 standard deviations below the assumed true value. I already can guess the area to the left of that, my p-value, it's going to be basically 0. But we can prove that to ourselves. So once again, we're dealing with proportions now, so we can go back to, whenever we see proportions, we can always use the standard normal distribution or the z-tables. So norm.s, I've got my test statistic. I want to find the area to the left, so .dist, tell it my test statistic, comma 1 gives me the area to the left. Okay. So this will give me my p-value. How would I find my critical values? Well, value or values. Well, for a left-tailed test, I'm going to have one critical value, and it's going to be negative, right? So here, what is my alpha? Well, at the 99% confidence level, my alpha is 0.01. So I know the area to the left. I want to work backwards. This is the norm.s.inv. I'll tell it the area I want to the left. That's all I need to tell it. And it gives me my critical value of negative 2.32. Right? Once again, I could use the if statement to kind of make this rejection decision. So equals if my p-value is less than alpha, then we reject. So if that is true, we reject, comma, if that's false, do not reject, or I think I was saying fail to reject earlier, same thing. Right? Well, now notice I'm way off here, so I could even say is half the population, 0.5, half the population white. Well, at that point, I can't reject, right? I'd fail to reject, but I can reject pretty high, like 0.55. I can reject that, given my sample. Now, one of the problems here is the data that I actually have here comes from something that oversampled kind of larger urban areas, and so automatically the proportion of white people in my sample wasn't reflective of the U.S. as a whole, right? Inner city New York does not look like Iowa, okay? So this was kind of a good example as well to relate to some old things we talked about, which is to make sure that our sample matches up with the population. We probably should have done some stratified sampling here, or something a little bit different. So this is how you would do hypothesis testing in Excel. Like I said, I'm not going to require you to use these if statements in your homework, but if you want to, you can, because I do ask you for the rejection decisions, and you can put those in there if you want. So I'm going to actually, since I have worked through a little bit of extra stuff here, I'm going to save this. I want to save this here, and I'll post this up on Canvas. So that you can have those if statements to look at. You can see the additional things I might have kind of showed you multiple ways to do it, and not just have the kind of nice and kind of tidy completed versions. Okay? So I'll put this up there on Canvas as well so you can see that. So that's how you do hypothesis testing in Excel. I looked at multiple different alpha levels here. You know, nice thing is if we reference these, I could actually then say, okay, instead of 90%, what if I wanted to do this at 99% or an alpha 0.01? Plug that in, it kind of updates my critical values. It would update my rejection decision if I could reject it, and then so on and so forth. So this is a really good template for the last two problems on your third Excel assignment. If you have any questions over anything I did in here, please let me know. Kind of the nice thing about this being recorded is you can pause and see exactly what I did in each cell.